Okay, lecture problem number 2. A person has a mass equal 70 kilograms, is climbing a ladder. Its length is equal to 6 meters. Its mass is 20 kilograms. The ladder leans against a smooth wall, which means there is no friction. Most of my questions related to ladders do not have friction with the wall. There is a friction, however, between the ladder and the floor, keeping it from slipping. The angle that the ladder makes with the wall is equal to 30 degrees, and the question is, what is the friction force equal to, so a person can go all the way to the top of the ladder without causing the ladder to slip. Since we want the system to stay at equilibrium, the first thing that should come to mind is the sum of the forces should equal to 0. For that reason, let's put together a free body diagram. The main force that we are familiar with is the weight of the ladder, straight down like this. This is M2G. There is also the floor acting on the ladder straight up. That's the normal force of the floor on the ladder, straight up like this. This is the normal force of the floor. I wrote it down in this form for easy reading. Now, there is a man who is going to go all the way to the top. I'm going to represent that man by means of a box. And he is acting on a ladder with a force equal F. That force is defined as follows: the force of the man on the ladder. That force is the same as the force of the ladder on the man, which is the reaction force. And since the system is at equilibrium, the reaction force, which is the force of the ladder on the man, is the normal force. That force is equal to the weight of the man. For that reason, I am going to simplify the task by representing the force of the man on the ladder by mg of the man, like this. M1g. So, one more time, the force is not M1g. It is the force of the man on the ladder, which equal the weight of the man M1g. Good. The forces which are acting horizontally on the ladder are the normal force of the wall on the ladder. Okay, I'm going to represent it by normal force due to the wall for easy reading. The other force is the force of friction, which acts towards the wall. Right? This is the friction force Fs. Using the sum of the forces equals 0, because the system is in static equilibrium, the x component has only two forces. Fs is positive and W is negative. They add up to 0. Therefore, the Fs is equal to NW. The y component has NF pointing positive, M1G pointing negative, M2G pointing negative. All of those, they equal to 0. Therefore, the force of the floor on the ladder is going to equal, move the mg's to the opposite side of the equation, you get m1g plus m2g. Notice that the normal force of the floor equals m1g plus m2g. Since m1, m2 and g are constants all the time, therefore the normal force of the floor, regardless where the man is going to be located on the ladder, that quantity always going to stay the same. However, what's going on with the normal force of the wall? When the man goes up the ladder, the push on the wall increases. What's going to happen? The reaction force from the wall increases according to the third law. NW increases, automatically Fs has to increase. As the man goes up, he causes NW to increase, Fs increases. If we reach a point where Fs reaches its maximum, we make sure we do not step any further up the ladder because the ladder will start slipping. Also, f of s is not going to be able to be solved here because we don't know what NW is. What do we need to do? We need to go to the sum of the torques. They equal 0 also because the system is at equilibrium. There are many torques here. I'm going to write down all of them. But before we do so, we need to make sure we decide about the axis of rotation. The two obvious points are either the top of the ladder or the bottom of the ladder. Notice that most people will think the top of the ladder is the best because by placing the axis at the top, you're going to eliminate NW from your torque equation and you will be able to solve for Fs. To be honest with you, the bottom of the ladder, if there is no friction between the wall and the ladder, is a better option. And the reason is, choosing the axis to be the bottom, sure you're going to eliminate Fs from your equation and you will be able to solve for NW. But don't worry about that, NW equals Fs anyway. So by solving NW, you have solved for Fs. Okay, so the axis is at the bottom, right here. The Fs will have 0 torque because the lever arm is 0, and F will have 0 torque also for the same reason. The two mg's are trying to turn the system along this line like this. However, the NW is trying to turn it the other way. This is a static equilibrium system. It doesn't matter which one of these two is going to be positive, but as usual, I'm going to choose the counterclockwise to be positive, the clockwise to be negative. Alright, so all the torques, I'm going to write all of them. There is a torque due to Fs. There is a torque due to NF. There is a torque due to NW. There is a torque due to M1G. And there is a torque due to M2G. They all add up to 0. Okay? The torque due to Fs and the torque due to NF, both of them are zeros because the lever arms for those two are zeros. One more time, why they are zeros? Because both of them are acting on the axis of rotation. Good. NW is the one right at the top, right here. Here is the NW. Alright? The line of action for NW is the following one. This dashed line here. The shortest distance from the axis of rotation to the line of action is this dashed line. Extend this line here all the way until you hit the line of action in a perpendicular form. Okay, so this line from the axis all the way to the line of action is the lever arm for NW. How can I solve for that one? That quantity is the same as the side that I have here along the wall. Using the triangle, I can easily solve for this part of the triangle along the wall, which is going to be L, which is the length of the ladder, cosine 30. The part that is on the other side here, it's L sine 30. I'm going to need that one in a minute. Okay? So the torque due to the normal force of the wall is the normal force of the wall times L cosine 30. M1G has a negative torque because it's turning clockwise. Here's the negative sign. M1G. The lever arm for M1G can be easily evaluated. The line of action for M1G is the following. I'm going to use the dashed line here for you to be able to pick it up. The shortest distance from the axis to this line of action is L sine theta. It's this quantity here. So the lever arm is going to be m1g times the lever arm, which is L sine 30. M2J, when it's extended, is going to split the base into two equal halves. Therefore, the torque due to M2J would be negative because it's turning in a clockwise direction. M2J times L sine theta divided by 2. This whole thing is going to equal to 0. Time for us now to simplify. This L, and this L, they're all going to cancel. Keep the NW term on the left hand side of the equation. Cosine 30. Move everything else to the opposite side of the equation. You can have M1 G sine 30 plus M2G over 2 sine 30. Divide both sides of the equation by cosine 30 to get rid of the cosine 30 from the left hand side of the equation. Cosine here is gone. The right hand side has sine over cosine, that is the tangent. Alright, so here is the final expression. NW is going to equal M1G tangent of 30 plus M2G over 2 tangent of 30. You can factorize the G tangent if you want. Let's do it to make this expression look very attractive. You're going to have G tangent of 30. What's left inside? It's just M1 from the first term and M2 over 2 from the other side. Solving for NW, which is the same as the friction force, Fs, we find 452.6 newtons.